Hello and good morning to Gauder Acoustic in Germany. I think you have been here on this channel for some times and seen some videos, and we always talked about loudspeakers or room acoustics or some effects which belong to the hearing. But today I just have a topic which is not directly related to what we sell, but it's a very, very important component of any hi-fi system. I'm talking about cables and especially loudspeaker cables. And you see from my selection there are different types of loudspeaker cables. And in the beginning of the hi-fi, it was only just a normal wire like this one with plus and minus. And now we have some more elaborate products on the market. And I want to talk about the physical basis of the transmission of signals from amplifier to loudspeaker, and that's the cable. So let's check what we can say about cables. Just like this one, the normal cable you see, which we all used in the 60s, 70s and 80s. And we have some physical theories about the transport of energy from amplifier to loudspeaker. And people think it's very easy, but actually if you take a look at the details, it's always the same. Things get complicated. And so my first question to the hi-fi customers is always, what about the transport of the energy from amplifier to loudspeaker? No, everybody tells me, oh, Mr. Gauder, that's easy. We have a cable, and in the cable there's the transport of the energy. And that's the first mistake. It's absolutely not the case, because we transport the energy from amplifier to loudspeaker not in the cable, but in the electromagnetic field which is surrounding the cable. So the energy is not running inside the cable, but outside. So that's the first surprise people always have. And then there are some effects coming along with this, which can be very, very tricky in hi-fi. And because normally we have our cables lying down on the floor from the amplifier to the speakers. And what we then do is that we ground the electromagnetic field. Of course, if you put the electromagnetic field on the floor, you ground half of the electromagnetic field, and then you distort the electromagnetic field. You can see this also from the transmission lines, which are transporting the energy from the power plants to the houses. And they are very, very high, and that's not because of the danger to touch them. It's because of the grounding effect of the earth. Yeah, what can we do? Of course, we use a thing like this, a pyramid, and put the cable on it. And so we increase the distance from the ground to the cable, and the electromagnetic field is running in air all around, and we have no losses due to the grounding effect. So if some people put their cables on things like the pyramids here, it's a good reason why. So that's the first surprise we have, and now let's check how a physicist is describing a loudspeaker cable and its behavior. We always have an amplifier and the wire, and then we say this wire is ideal, and the cable is described by an ohmian resistance. In German we use this symbol, therefore, and we have the value of R for resistance. The next thing is we have an inductance here in this cable, and I always like to use it like that, the symbol, because that you can see that's coil. And we denominate it with the letter L. What we also have is, of course, this cable has a capacitance. And it's across the wire from plus to minus. So we need to take the capacitance here from plus to minus. Also, yeah, you can see maybe there is some energy transported from plus to minus through the air. And that's what we call a conductance. It's a resistance which is parallel to the loudspeaker. So, that's how a physicist is just describing the behavior of a cable. We say here capacitance C, and the conductance is called G. These are the four components which describe a loudspeaker cable or any cable in the physical world. Now let's make some discussion about it. I have a loudspeaker here, and normally a loudspeaker is something like 4 to 8 ohms. And if we check the capacitance of a cable like this or like this, we have values which are much, much higher and which are 10,000 ohms or something like that in the normal audio range. And so in audio, for a loudspeaker cable, we forget about the capacitance, and also the isolation of these cables between plus and minus is very, very good. So we have a very, very high resistance here, 10,000, 100,000 ohms. And so we can neglect these two components compared to the loudspeaker, which has 4 to 8 ohms. But still we have the resistance, the resistor R, and the inductance of the cable L. And they are in series to the loudspeakers, and of course they make an effect. And how can we describe this effect? Just I take some other color. We can say, okay, this is a low pass filter with a special time constant and a cutoff frequency. And we can calculate it by this, the time constant of the cable here, tau, can be calculated by L divided by R. This is a typical value for such a cable, and we can describe with this value the behavior of the cable in the frequency range. Just take a look at this L divided by R. So if we have a high inductivity of the cable, high inductance, then the time constant gets up. We have a high time constant. Also, if the resistor R is very, very low, so for example, if we use a very, very thick cable, then the ohmian resistance is very low, and then the time constant gets up too. Okay, so let's check what we found out. So if we have a time constant tau and the cutoff frequency Fc, then you can calculate by easy mathematics. It's 10 microseconds correspond to 628 kilohertz. So you see 10 microseconds, that's nothing. So 628 kilohertz is far above the audio range. A cable with 10 microseconds time constant is not making any effect in the audio range. But let's go on. Let's think about a cable with a time constant of 100. microseconds. Yeah, and of course, it's a factor of 10. We have 62.8 kilohertz. You see, our hearing is going up to 20,000, so 20 kilohertz. So it's not far away. Maybe this is already making an effect. And what's the effect? I just show you here this in the small diagram. We have the frequency over the amplitude. And if the cable has a very, very high time constant, then in the audio range nothing is happening. But then there is a special cutoff frequency, FC, which is already 3 dBs down the regular transmission. And so if we have a FC within the audio range, that would be not very beneficial. Of course, then we get distortions and we cut off the high frequencies, and also we delay the high frequencies. Let's go on with a value of 1000 microseconds. And now we have 6.28 kilohertz. So now we have the case with such a cable that the frequency cutoff point is within the audio range, 6.28 kilohertz. So such a cable would transmit no high frequencies to the loudspeakers. And we cannot use such a cable with such a high time constant. And the next thing is also very, very important. I always talk about frequency response and impulse response. And some people just are not very, very creative with this thing. They say it's okay, it's just not a big deal. But here we have the big problem that we have a phase shift and we have a delay and of this low pass filter. And if we check the impulse response, normally we have such an impulse, and now with such a cable we have an integration, and then the impulse is totally distorted and dampened. And if you compare such an impulse response original to impulse after the cable, you can see we should not do that for a high-end system. Yeah, once again, it's not only the frequency cutoff, it's also the distortion of the impulse. And so a cable with such a high time constant is just distorting the signal and dampening it. Yeah. No, okay, that's no problem, you say. 10 microseconds. Is it possible for a cable? Yes. Not for such a cable. Such a cable is always around 100 microseconds. But a cable like this and a cable like this is just really a good deal for getting such a low time constant. Because you can see here we have a plus and minus wire and they are drilled. And so the magnetic fields cancel. And that's why the inductance gets low. So that's a low inductance cable. And with this here, it's much more sophisticated. We have 8 wires plus, 8 wires minus, and they are just drilled all around them. And so the inductance of such a cable is very, very low. And for such a cable, we have 10 microseconds time constant. Yeah, and we look at this cable here again. It's 100 microseconds around this. But if I would increase the distance between plus and minus dramatically, then of course the magnetic fields cannot cancel anymore, and such a cable is just going up to 200 microseconds, 300 microseconds, and then the cutoff point is coming into the audio range, and we have a frequency cutoff, so we have no high frequencies, and we have a distortion of the impulse. This can not be very beneficial for a hi-fi system. So always keep in mind to have a low inductance cable. Yeah, what else can we say about loudspeaker cables? Of course, there are some more effects, like the skin effect. Skin effect is something which is very, very important for high frequencies. And we found out with a special diagram that also in the audio range, starting up at 2 kilohertz, we can see a skin effect of big cables. The skin effect is just something what we can show in this diagram. That's our wire, and we look into the wire. And normally for low frequencies, all the area is used for the flow of the current. But for high frequencies, just the electrons make the big move outside, and then the current is only running on the skin of the wire, and that's why it's called skin effect. Magnetic fields cancel each other here inside, and the magnetic flow and the flow of the current is just only on the outside. And then we have a higher ohmian resistance, and the time constant changes with frequency. And that's also not very beneficial, not very good for hi-fi. We need a constant time, constant here of the cable, and not a frequency-dependent time constant. So big cables have big disadvantages. And when we started hi-fi, we started with a very, very thin wires. Then we got some more like this one, just medium. And then some people tried to have big cables. And what they found out is just it's not getting better with the big cables, with the thick cables. It's getting worse. And now we know why. The ohmian resistance R is getting lower for big cables, and so the time constant goes up. That's very tricky. You have to think about it. If you use a big wire, then you have a low ohmian resistance, and then the effect is that the time constant tau is rising dramatically. We then go up to 100 microseconds or something like that. And then we distort the audio signal. So we need a good compromise, not too thin and not too big. The next thing is we can talk about the magnetic distraction of two wires which are very close to each other. You know, if we send current through them, and then the two wires distract them by magnetic forces. But this effect is just for normal hi-fi cables. It's about 10 to the minus 5 Newton. So the force is not very, very big. But of course, if you think about some cables drilled, maybe they can be modulated and they can vibrate a little. And it's like all the things we discussed before. We have a lot of effects. But if you can hear the effects, if they are really effective for distorting the audio signal, that's always a good question. How big must an effect be to be detected by the ear? But as you all know, our ears and our hearing system is very, very sensitive. And this sensitivity leads to the thing that we hear every change in a hi-fi system. If you have a good hi-fi system at home, and if you are used to listen to the system, then if you change a cable, you can hear the difference. And so our ears and our hearing system is just very sensitive, and we have to be careful with this and have to check if all the effects are really affecting our transport of the signal from amplifier to loudspeaker. So you see, we can tell a lot about the effects of all these parameters of a loudspeaker cable. The same is true for signal cables, RCA cables, which connect any source like a CD player or streaming to the amplifier. But as the input resistance of an amplifier is about 20 to 30 kilo ohm, it's totally different, because we have in a loudspeaker system in 4 to 8 ohm, and amplifiers have an input resistance of 20 or 30 kilo ohms. And so the discussion is totally different. We don't need to check the ohmian resistance or the inductivity of the cable, because there is a big resistor in the back, and you can neglect these two components. But now these two components, C and G, get important, and we can do the same discussion with C and G here instead of L and R, and can make a time constant for an RCA cable too, and can make the same discussion like here with the audio cables. But that's not a big problem, because the capacitance and the conductance of any RCA cable is so perfect that we have a cutoff frequency which is around 600 or 1 million hertz. So nothing for the audio range. And therefore, RCA cables are not that sensitive for the sound of a system like the loudspeaker cables. So that's the story about loudspeaker cables and RCA cables. I will make a second video concerning this topic, and I will talk how we can build the perfect loudspeaker cable according to all the knowledge we have now gained. And if you want to see it, I refer you to the next video. And I hope you all enjoyed this physical excursion to loudspeaker cables. And I would like to say, there are not the big effects, but if you have a good system and you are used to the system, you can hear the difference of changing cables, and you can also hear the effect of the pyramids. Some people say that's big nonsense, it's just small deviations only. No, okay, that's an opinion, but if you have a very good high-end system, you hear the differences, and then you must estimate and check if you are really able and ready for buying a big hi-fi system cable, which can be very expensive, I know. And but you always have to keep in mind what we talked about. And if you have the values of L and R for loudspeaker cables from your producer, you can easily calculate the time constant and the cutoff frequency. And so I would like to say thank you for listening to this video, and I hope you all enjoy your system, even though you have heard now a lot of things about physics of loudspeaker cables. Goodbye.